you said.
You got it?
Yeah.
Okay. Okay, good.
So, he didn't know, I didn't know, this was an international event, so like 800 abstracts. So, more than half of them were married. So then he ran the cancellation. And like, I'm going to dim the lights.
Okay, everybody, we're going to get started because we don't want to have any less than as much time as we can have for this presentation. We're very fortunate today to have two people who have had very much to do with the James Webb Space Telescope, and we will find out much more from them about what led up to it, how it's been commissioned, and some first results. So the two folks we have with us today are Neil Rowlands and René Doyon. I'm going to very briefly read a few words about each, and then we can get right into their presentations. So Neil Rowlands obtained his BSc from the University of Alberta in 1985, his PhD from Cornell in 1991. At Cornell, he developed infrared instrumentation for the Kuiper Airborne Observatory and the 5-meter Hale telescope at Mount Palomar. Cutting to the chase, he is currently an engineering fellow at Honeywell Aerospace, based in Ottawa, Ontario. René Doyon is a full professor in the Department of Physics at the University of Montreal, Université de Montréal, pardon, and is the director of the Institut, well, let's do this, Institut pour la recherche sur les exoplanètes, plus ou moins, and the Mont Mégantic Observatory. His research activities are focused on the detection and characterization of nearby exoplanets and the development of state-of-the-art astronomical instruments for ground and space-based observatories. So there's more, of course, and once their presentations are over, I'm sure you'll want to spend a little time chatting with them. But at this point, I'd just like to turn things over to Neil, who will be the first of our two speakers.
Thank you. Thank you very much. So if I could get the first slide. Oh, here we go. No, I should be mic'd. So yes, I wanted to talk to you today about the first 25 years of our Canadian experience on JWST. Next slide. I'll tell you why it's the first 25 years in a minute, but clicker. Yes, sorry. Here we go. Okay, so this is a real quick summary. I'm going to try to give you a whirlwind tour of the development, talk a little bit more about the commissioning, especially of the guider, and then René is going to take over with some of the fabulous results. So, as everyone knows, I think the Hubble the James Webb is the successor to the Hubble, named after a NASA administrator who tried to get a lot of science into the Apollo missions back in the 60s. So it's much bigger with a 6.6 meter diameter collecting area, deployable mirror, passively cooled to 40 Kelvin, or what is that, minus 230 degrees C, and working in the infrared. And it'll detect and characterize first light sources. And we're talking today about Canada's contribution, which is a fine guidance sensor and this instrument called NIRISS, a near-infrared imager and slitless spectrograph. So, but not to forget that we also have Canada contributing to the commissioning and operations of this telescope, and of course to the contributions to the Canadian science programs, because now we have 5% of the telescope that gets to be allocated to Canadian astronomers, hopefully for the next 10 plus years. And it is Canada's largest space science project to date, approaching $200 million Canadian. So what it's about, and some of the, going way back in time, Simon Lilly at the University of Toronto at the time contributed to some of the early studies that NASA was doing, and also was instrumental in convincing both CSA and the Canadian astronomy community to get involved in this project, because Canada has used and taken advantage of data from the Hubble, but it was not involved in any of the hardware contributions. So the justification for JWST is centered on first light. And that is basically looking back in time, sorry. I guess I don't have a laser. Looking back, if this is the present day and we look back, as we look deeper into the universe, we look back in time, all the way back to the Big Bang, which would be here, but this is the cosmic microwave background radiation. And when that, space missions have observed that, but what's in between that and the present day universe has been unclear. Hubble has probed some of it, but JWST is its goal. That's the first light machine, is what the name of the telescope was. Technologically, that was actually a really good fit, because if you're in the infrared, you can make better use of deployable optics. You don't have to be as accurate in your deployment. And also, your contamination is less of a concern, so you could go with that open design. Disadvantage, you have to have cold instruments, cold telescope, and advanced detectors. But that was all done. But how did we get there? So this month, 25 years ago, we submitted our first proposal. It was a collaboration between us at Cal Corporation at the time and NRC to look at a multi-object spectrograph. That instrument was eventually provided by ESA to the mission. Then in 1999, this technological symposium was held, and coming out of that, 3 instruments were selected. NIRCam, NIRSpec, and MIRI were selected at the time. There was no NIRISS. So along the way, it turned out that guiding was supposed to be done at NIRCam at that time. But then they realized the science filters were not really compatible with the guiding function. And lo and behold, John Hutchings of NRC stepped in and was able to convince NASA that a separate guider was needed, that it wouldn't be too large. Canada could do it. Canada could do it because we had done experience with the Fuse Fine Error Sensor. This is a far ultraviolet telescope that was launched in the 90s. And we also developed on our side, we had developed this star tracker called CalTrack. These are all items that basically do find guidance, say, to track stars. So that's how we got into the project with a guider. And we also were successful about convincing NASA that there should be a science contribution, and that's how the tunable filter imager came out, and René was able to work with the University of Arizona on their NIRCam concept, which was selected, and therefore we moved into the development phase with that in 2004. So we had a bit of a rocky start to our phase C. We had to redo the design because NASA was worried about mass. So we had to rescope the TFI channel, go to 1 channel instead of 2, and do other things like we lost our computer that we would have been doing the guided processing in. That actually went into the NASA computer. But we were still able to deliver in 2010 a test unit, and then in 2011 we had development difficulties with this tunable filter shown here. It became obvious that we just weren't going to make it in time. And fortunately, René had a great backup plan called NIRISS, and the project agreed, implemented that in a year, and delivered the instrument. And it was the second instrument delivered to NASA after the mid-infrared instrument. So quick summary, I mean, you've all seen pictures of the telescope. I just wanted to locate the Canadian contributions. We have the instruments in the back here in this integrated science instrument module. That's where they all sit, including FGS NIRISS optics. But we also have, well, on the next slide, you'll see the layout, but I just wanted to point out the key elements, the primary, secondary mirror, and then in here we have a tertiary mirror and a full fine steering mirror, which is very important for the guider, and then back to the science instrument. So here's, without the sun shield on, you can see more, and this is a stripped off version of the ISOM, and we have actually warm electronics here, even though they're behind the cold shield, and that's where our fine guidance sensor NIRISS electronics sit. And of course, as I mentioned, we lost our computer, so we have our processing is actually happening on the spacecraft side in the ISOM command and data handling unit. So those are the 3 main components. I mentioned that optical system. The green is the light path. And what our job is to sit in the focal plane, which is over here with the other science instruments, and to monitor the star field and give that position to the attitude control system, which then drives the fine steering mirror and stabilizes that line of sight for the other science instruments. So all the images you're going to see from JWST are all when the guider is operational and stabilizing the line of sight. We also have to track stars, and I'll talk about that in a minute, to do the moving object observations. And then one little fun fact, if you like it, René and I disagree on which one's the better metaphor, I guess, is we can track tiny angular displacements, so the thickness of hair seen from a kilometer away, or if you prefer, seeing somebody blink in Toronto when you're standing here in Montreal. So, pick whichever one you like. But keep in mind, we do have this very large telescope in front of us, which helps us get that angular precision. So here's the field of view of the overall telescope divvied up, and I would quite proud to say that Canada owns 40% of the field of view of James Webb, which is pretty amazing. Of course, most of that is dedicated to the guider function. In fact, in the early days of studies, that guider was going to, both of these guiders are going to be 4 times the size until John convinced them, John Hutchings, that they really didn't need that large field of view. But nonetheless, we ended up with a large field of view. And we divided that into 2 very large infrared detectors fed by common optics. So I won't go through it here, but there's a picture of the optics. And these are the 2 detector modules here, side by side. On the NIRISS side, we have 1 detector. There's the optical path. And this is the key element, is a dual wheel where we place different optical elements to do the science that René is going to talk about. And this is a quick summary of the 4 operating modes. René is going to cover, I believe, mainly the wide field slitless spectroscopy and the single object slitless spectroscopy mode. So I'll let him talk about that. But suffice to say, it just depends on which elements in the filter wheel and pupil wheel that are selected to do those observations. Okay, so now, if I'm not going fast enough, I'm going to speed up even more. The build and test. So we went, well, this is the electronics unit being put together. This controls both guiders, independent electronics, but housed in the same housing. And then the NIRISS. So the NIRISS has an extra card, I think it's this one, to control the dual wheel, a lot more motor control electronics. And as I mentioned, it sits in a different environment. It sits in the warm ISM electronics compartment, and therefore we tested it separately. So it gets a different vibration test, a different thermovacuum test, and we also had to test for EMC. Obviously, we want to make sure that we can meet our noise performance, which was a challenge because the EMC test is normally done at room temperature. We don't have a cold detector to verify that end to end. So on the optics side, I just want to point out a couple things. We have an all aluminum instrument, which helped in terms of the development, but we did have to isolate the instrument from any perturbations that could disturb the objects. So we have an optical bench, and then the 3-mirror system sits here on top of that. But we also have titanium legs, which interface to the graphite carbon epoxy structure of the ISM. So this transition from a almost 0 CTE material to the aluminum. And then we set it up to, optically we set it up without the detectors first to do a pupil alignment. I mentioned that fine steering mirror. That's actually 3 meters away. So we, that is the pupil, the entrance pupil of the instrument, exit pupil of the telescope. So we had to test that. We had to fold that path into the, so that we could do the testing in the chamber. And that's shown here with these large fold mirrors here where we set up to do the pupil alignment test to make sure that we're actually looking in the right place, as well as making sure the detectors are in focus when we got them. So then we did a full up testing, vibration test, and as I mentioned, the cryo test. But in this case, this is some simulated sources with some stray light in the chamber. And actually, I've mentioned ABB. They developed the OGSE, the optical ground support equipment for us. That's this set of large number of telescopes which provided us with the point sources, including one moving one, where we could test the guiding function. So then we finally delivered to NASA, and we can see here the first 2 instruments, MIRI and FGS. And then we see the full ISM on the right, where you have the near-spec instrument, this large foil covered, and then the NIRCam instrument goes in front of us. So we're kind of the first in, last out, which was lots of fun when we had to actually replace the detectors because the detectors were degrading. So a crew went down. This is our crew at NASA Goddard, working over Christmas, of course, to replace the detectors and also make some improvements in the NIRISS optical components. So that gave us that opportunity. So that all went well. And then we went into the 3rd cryo test down at NASA. That's shown in this chamber here on the left. And the ISM went through its own vibration test. And then up the upper right there, we have the observatory, or the telescope element plus the ISM preparing for vibration test. And And then the whole thing went to NASA Johnson in the lower right here, where first optical tests through the entire telescope and to the instruments was performed. And we were able to finally verify at that point that the fine guidance sensor will actually give the right commands to the fine steering mirror to actually do what we needed to do. Oh, by the way, that was all during Hurricane Harvey, of course. So then I just wanted to make a call out to, you don't do a project like this without a lot of people involved. And here are some of our key suppliers across the country and our US partners. And then here's the group at the delivery from the David Florida Labs in the center here. And then down on the left there, we have the group involved in commissioning the telescope. We had to go through numerous exercises and rehearsals to do those operations, of course, during a pandemic. So that was all fun. But it involved everybody from CSA, Honeywell, University of Montreal, National Research Council, NASA, and the Space Telescope Science Institute are all represented on our guider team. So it's a team of about 30, 35 people. And then launch. And here's René and my colleague Dave. Got the chance to go down to Kourou for the launch, and the beautiful send-off we got from the Ariane 5 rocket, which actually was really important because it was such a nice trajectory. All the mid-course correction burns worked. So when you add up all that extra margin, that's when people started to get really excited about 10 plus years of operations. I should say, it was designed for 5, margins are supposed to carry it at 10, but when you add all the margins up that everybody carried, it should go even beyond that. So then we talk about commissioning, and I just want to make sure I have not taking too much of René's time. So I'm just going to talk about the guider commissioning. And again, this is the team on hand on January 28th when we powered up. I should mention at this point, a lot of the hard stuff has already been done, right? NASA launched end of December. The Northrop Grumman team was there for that first month, around the clock, was actually able to deploy the primary mirror, deploy the sun shield. So it all worked, and then we could actually just flip the switch and see if guider worked. It did, thank goodness. Everything was done as the telescope cooled down, which is one of the things that's blown my mind about this whole process, is they had such good control and understanding of the primary mirror segments during those ground tests that you could actually make adjustments while the thing was cooling down, because the thermal models were so well designed that you could then predict where it's supposed to end up. So it was really phenomenal to watch that happen, and I'll discuss that a little bit more. But the milestones for us were functional aliveness tests. We were still warm, and we were worried about hot pixels. It seemed to be a bit more in test, but it was early days, and it turned out not to be a concern. Then we had our first closed-loop guiding, which was a major milestone, successful fine guiding, moving target, and then finally, basically, there was the NIRISS also was doing tasks all the way through, and they were fully commissioned. The first instrument to be commissioned June 22nd. This is just an example of dithering. I don't know if there it goes. So in this case, we just moved the fine steering mirror slightly, and it moves the centroid. These are the centroid locations. The cloud, you can see that there'd be jitter. Oops. Here we go. I don't know if I get it to run again. But anyway, you get the impression it was jittering in each point, but then it was also moving about half a pixel as it provides these centroids. That's important for the science observations because I'll talk about hot pixels in a minute, but all the detectors have hot pixels, bad pixels that they need to. It went, okay. Okay. Well, I just wanted everyone to see that again because it went by fast. So we have to dither, which means you change the field of view slightly in a controlled way such that you can remap or take out the hot pixels that the other science instruments have on their detectors. So you don't want your prime science target to be sitting on a hot pixel and then not move the telescope slightly. So dithering is important, and the guider supports that function, and it's one of the things that kept me up nights through this whole process was how accurate the dithers are going to be. And at the low level and when the star is bright, it was working very well. I should mention the size of this cloud is what I refer to as noise equivalent angle, which is another important metric because we don't want to jitter too much, otherwise we degrade the science instrument images. So this is the flow of how they got to aligning the telescope. The guider had to support this. A clue, for example, is where you see an image like this, where one segment has been shifted off. And the reason is that was the star, or that was the segment with the guide star that we ended up guiding on to facilitate the process of getting all those segments lined up. So the first, they got to the fine phasing part, and then got this beautiful image of a star, but then they needed to check that all the other science instruments across the field of view had the right image quality, and that's where that image was released. So as part of that, just to show you, that was one of the first images they call segment identification. They were all akimbo, they were all not aligned. They could identify which segments were on the wings. And then once they did that, they could stack them all, but you can see each segment is not well focused or aligned. But nonetheless, at this point, they wanted us to start guiding. So we had a track mode, and this is one of those segments where we're now following it around and actually producing centroids so that they could adjust the line of sight, stabilize it enough to start tuning each of those segments. And then they did such a good job, it was too good. At least I started to really worry about it, because if you get too focused an image and you do that dither and you shift, you can introduce a systematic uncertainty in that centroid location. And if the image is too sharp, and they were sharper than we expected, we may have a problem. So guider was actually the only instrument that changed its focus as part of commissioning. They did such a good job in the rest of the telescope, even though they're carrying focus mechanisms in NIRCam and NIRSPEC, they didn't have to use them. They just aligned the telescope, and it worked. They were all happy with the focus, which is pretty incredible. But we thought it was too good. The other, I mentioned noise equivalent angle. I was thrilled to see these types of data where this was coming out of all our test campaigns. And we actually had trouble when we got to the big chambers down at Goddard. The noise equivalent angle, as you take the amplitude, the star brightness goes up, you're really just getting rid of the noise and you see what's happening. And that basically we were around 1 milliarc second. But we knew from our instrument test, where we had a quieter chamber at DFL, that we could do better than that. And indeed, on orbit, that's where we ended up. That data is coming from various guide stars down at the half milliarc second level, which is really good. That's us in the control loop, providing that information. Whereas the jitter ball, this actually is data from NIRCam. Almost all the time they're coming up with about 1 milliarc second jitter. The overall budget for this was about 7 milliarc seconds at the system level when you count everything and look at the science instrument. So talk about margins, it's great. We're doing very well. And more importantly, this is with the MIRI crowd cooler on, so we didn't have to worry about that. And then there was moving targets, which were a thrill for me. So what you just saw there, if I can play it again, I'll go back. I knew it. One more back. Okay, there. This is the NIRCam image of an asteroid. And of course, it's moving against the stars. So what we have to do is move a guide star to compensate, and then it stays centered in NIRCam. And if you were looking closely, it actually wasn't quite centered. This is their whole data set from, this is the very first moving target tracking run, asteroid Tenzing. And you could see it jump, and that was actually dithers while we're doing moving target. So it was kind of cool to see all that happen. And then this one I show here, this is a faster moving target. This is kind of pushing it up to 1 pixel per second almost. But you can see our hot pixels. Every time they move, we're updating our window location to follow the guide star. And occasionally we come close to hot pixels and we hope the software is masking them out properly. But this is a great data set for analyzing how the guider performance is. And it really helped me calm down about the dither accuracy, because it turned out we're covering a lot of the array. These are the X and Y values over time. So we cover a lot of the array. And then if we look at those linear plots and subtract a linear fit, we see all sorts of interesting things. So first of all, there's the settling as you first start tracking. Then we cross a bad pixel. Then NIRCam moves some mechanisms, so we see some jitter. And then a NIRCam exposes, and during that we crossed a bad pixel. This is quite small. I mean, it's 10 milliarc seconds here. Most of the time we're really good. There's only so much we can do to correct for hot pixels. But what was also really neat is if you really zoom in, is actually a 2 milliarc second oscillation. And that's that offset in the centroid that I was so worried about, and it's at the right level. So that was, and the Fourier transform proves it. So that was great relief to me to see this data. And then finally, I can't resist but to show we took advantage during commissioning time. There's a long thermal settle test. We actually get, well, one of them, the earlier test of that was only a half-hour integration. The next one allowed us to do a 32-hour integration with the guider. And this is false color. I keep flipping between color palettes here, but you can see a lot of structure in here, and I zoom in a little bit. And there's just some, to me anyways, there's just amazing groups of clusters. And this is a broadband image, but it is the most sensitive because it's the broadband. So the question is, what can we learn from this? Maybe not much yet, but once NIRCam has figured out, and the other instruments have figured out what the right magnitude and what scale size we should be looking at for first light objects, for interesting objects, then we're going to, maybe these images could be of great use. Anyway, that was my pitch to do science with the guider, which hasn't happened yet, but could. And with that, I'm done for my section, and René's going to take over and show us the real stuff, the real science, not this. So we'll switch.
So if you can move to the other presentation. So Neil gave you just a glimpse of the complexity of this observatory. So what I'm going to show you is show you some example of the science that the JWST has been doing so far. I'm really pinching myself because this is my 21st anniversary of involvement in James Webb. I've been giving talks for years about what James Webb is going to do. And it's disturbing to think that right now, this thing's observing. It's out there. It's taking signs, and amazing signs, as you'll see. Okay, so I just want to acknowledge that many of my slides come from my colleague, Nathalie Ouellette, who's the actual outreach scientist, outreach scientist, paid half by CSA to do this, and she does beautiful slides, and I just borrow from those. Okay, so this is our instrument. Neil showed it, FGS, and the NIRISS on the back. We could spend hours about the history of NIRISS, but it got very close for this instrument not to be there. But it's there and it's doing great science. Okay, so Webb will do 4 things, basically. I'm going to walk you through those themes: alien worlds, life of stars, how stars form, how galaxies, how they evolve with time, and of course the early universe, which was the main part, the main motivation historically to observe with Webb. So I'm going to start by alien worlds, and first by mentioning that we were not planning to do that in the first 20 years ago because there was not enough observations of those. But right now, this science case represents more than 25% of observing time and a major fraction of the Kenyan instrument time. Okay, so we're very much interested by a very special class of exoplanet, transiting exoplanet, those planets that happens to go in front of their stars. And what you see, of course, you don't see that image, but you measure the brightness. And so you can easily measure the depth of that feature. So the bigger the planet is, the deeper the measurement is. So you can measure that fairly easily, even on the ground, even with a small telescope. But you can do more than that. And imagine now your planet has an atmosphere, okay? And then you're capable to do spectroscopy while the thing is actually going in front of it. And if you imagine molecules blocking lights in the atmosphere, there will be some wavelengths, some colors where the planet appears bigger. And so by measuring the transit depth at various color, you get actually a measurement of the atmosphere. Not only that it has an atmosphere, but its chemical composition. This is a powerful technique that, again, we were not planning to do 20 years ago because the very first transiting exoplanet was discovered in 2001. That's when I joined this project. So just to show you how things have evolved over time, and in fact, the problems that we got with NIRISS over time became an opportunity because in the late 2008, 2009, we realized that, hey, we could reconfigure our instrument into something that would be much more powerful, and that became this. So Transit spectroscopy, detecting exoplanet atmosphere, is one of the main science objectives of the NIRISS instrument. It was uniquely designed to do just that. That's one more. There's that 4 I won't have time to go through all of them, but I'll come back to this. Okay, so this is the very first observation that was taken in July 12. You've seen all these beautiful images, and I thought of the ERO's early release observation. That was July 12th, and the idea here was to give some representative observations of the science of the 4 science theme of JWST, and also for the 4 science instruments. And until 2 days before that, I did not know what would be observed. I spent 6 months, not 6 months, but several weeks at Space Telescope Science Institute looking at data with Neil, and we could see the schedule. Okay, here's on the ERO for NIRISS, but I did not know what it was. It was a big secret. I had some guess what it would observe, but finally they observed that thing. This is a hot Jupiter, and this is the actual data. So you can see what I meant here. This is the real data, and this is the transit spectrum. So basically the transit depth as a function of wavelength colors, and you can see these waves here are the spectral signature of water. So we knew there was water on that planet first, but this is the kind of observations that the Webb instrument, that the NIRISS instrument does. And just to give you an idea of the improvement, this is what HST used to do. So you can see we have a much broader perspective, a lot more data in wavelength coverage, and that's just one instrument. There's also transit spectroscopy capability with NIRSpec and NIRCam and MIRI to do this kind of science. Okay, now moving on to star formation. I'm sure you've seen these beautiful images. This is an example of a star formation regions, the Carina Nebula. This is the previous image was from Spitzer. This is taken with NIRCam here, and we see all kinds of things here. Newborn stars, dust that are pushed away from the very bright stars that are out of the field of view here. This is the image from Hubble. And it was a beautiful image, right? There was some doubt that, Webb would deliver beautiful images. Well, I guess now you know that he can do it, right? What really strikes you here is the resolution. We see a lot more details. That's really reflects the fact that Webb is a much bigger telescope. The bigger your telescope, the finer your images. Okay, so this one is a planetary nebula. This is basically the fate of the sun. So in about 4 billion years, the sun will run out of hydrogens, and then it will expand, and it will expulse the yellow layer. And what will be left there in the center is what we call a white dwarf. And there was a surprise here. This on the left, this is the image from NIRCam, and in fact here in the middle is actually 2 stars, and that probably explains pretty much the structure we see here. So there's a red dwarf in there, and one thing that also that is very interesting to note is that this little thing here that we thought it was an artifact. Oh no, of course it's a galaxy. Every image you take with Webb, and that was the thing we were seeing during commissioning. Any 1 minute exposure, you see galaxies everywhere. And there's so many of them, and it's all everywhere. Okay, so speaking of which, interacting galaxies. So this is a famous Stephan's quintet. So here what you're saying is interacting galaxies that are basically in the process of interacting and even colliding. And this is a beautiful image taken with NIRCam. You can see here the gas, which is shocked because of these interactions, and that compressed the gas, and this is where you have what we call starburst phenomena. So formations of lots of stars in this region. This is the MIRI image of the same view, and MIRI gives us a new perspective. The near-infrared instrument, NIRISS, NIRCam, NIRSpec goes from 0.6 to 5 micron, whereas MIRI covers 5 to 28 microns. So to give us new perspective, dust content. And so in particular, this galaxy up there where we know has a black hole in the middle, and so we can probe the inner region much better now thanks to MIRI, because we can probe through the dust. Okay, now the deep field, that was a big observations done with Webb, and all 4 science instruments contributed to that region. So what you're looking here is a galaxy clusters. So you can see the main galaxies in the middle. And you can see all these arcs, red arcs, that are basically galaxies in the background that are magnified by the cluster, because we know there's dark matter in there, and Einstein taught us that light actually is bent by mass. Yeah, so again, so many galaxies. But first, before I talk about the lensing effect, on the left, this is the visible image that was obtained with Hubble. And you can already see that you see just more of these galaxies with Webb. And that was only 12 hours worth of observations. And I was actually surprised when the first image came out. I said, really? So we're beating the best image ever obtained with Hubble, with weeks long of observations. But of course, when you do the math, you realize, yes, it only takes 12 hours to beat Hubble with James Webb. And of course, we're going to do much deeper observations. They are actually on the way. But just to illustrate to you the incredible power of this observatory. Why these galaxies are red? Well, it's because of the expansion of the universe. As the universe expands, any length gets larger, including the wavelength of light. So this is why these galaxies appear red. In fact, in reality, they're very blue. They emit the bulk of their energy at ultraviolet wavelength. But because of the expansion of the universe, they become extremely red. Okay. So let's zoom in this region here. There's so many details in there. Already lots of papers being published. And one recent one was from a Canadian team. You see that little thing here? So this is a galaxy in the background that has been magnified. And these little dots here are actually what we call globular clusters. But we now think they've been formed something like 500 million years after the Big Bang. So I'll remind you, the Big Bang is 12.8 billion years old. And so the NIRISS observation was actually critical here to tell us that this thing is actually young. There's lots of emission lines in there, but those dots, they do not show any emission lines. So an example of how you use various instruments together to get a picture. So this data was actually published in May. Okay, so yeah, I was explaining all these arcs, which are basically due to the lensing effect by the clusters. So you have, imagine a galaxy in the background that gets magnified. In fact, you get multiple images, in fact. And we actually tested that with NIRISS. So NIRISS can do spectroscopy like NIRSpec. NIRSpec does it by little slitlets, which is much more efficient. But NIRISS, this is why we call it a near-infrared slitless spectrograph. We take spectra of everything in the field of view with less sensitivity, but we get a lot more of objects. So typically, NIRSpec will observe about 100 objects in one shot, whereas NIRISS in a cluster of galaxies can look at thousands of those. And so here, this is a galaxy that we suspected to be the same galaxy in the background, to be analytical. And by looking at the spectrum, thinking about NIRISS, indeed, the two are analytical. That's a proof that this is indeed a galaxy in the background that is magnified and distorted by the gravitational field of the cluster. Okay. Very recently, there was another observation made by Webb. This is the Hubble image of one of the most distant galaxies ever found by Hubble. And the image with Webb now, I've shown that this thing that was looking like a single object, actually there's two. And the amount of swimming time needed for this thing was way much less than Hubble. And that's a very recent observation. So again, the 1, 2, 3 are actually, this is the same galaxies that is magnified and distorted by the galaxy cluster. So we're going to spend half of our guaranteed time observation in NIRISS to look at these kind of clusters, observation that actually just started. Okay, now what else can we do? Well, of course, solar system. This is a beautiful image of Jupiter, and you may think, oh, this was done, by these NASA experts and things. No. It was actually this young lady, a citizen scientist. She's been analyzing Hubble and now Webb data for quite a while, and you can see she's pretty good at it. So all the data are public, and you can look at it if you want. This is another one from Mars. And we can get a spectra from NIRSpec. You can see the spectral signature of CO2 in there. This is one with Neptune's beautiful images of the rings up there. And you see that image looks like easy, right? But Neil showed you how complicated that is, because this thing is moving, and we need to keep track of this thing very precisely. And that's, that's what FGS does extremely well. Okay, now I'm going to go back to transit spectroscopy because this is a new observation that was done recently, again, on a hot Jupiter, a discovery that was partly analyzed by people here at the Université of Montréal, my colleague Björn Benneke and student postdocs. So WEF 39 is a puffy planet. So basically, it's a planet that around a star about the same size as the Sun, but the planet is very close to its star with an orbital period of about 4 days. Mind you, Jupiter is 12 years. Okay, so its temperature is very hot. It's very hot. We call it a hot Jupiter. But it's only a quarter of the mass of Jupiter, and yet it's much bigger than Jupiter. So it's a low-dense planet, and low-dense planets gives very strong atmospheric signals. So it's not a coincidence that we pointed the telescope to that one. And so this is the previous observation that had been done with Hubble. So you can see these, again, the data. This is the transit depth, and the data points is from Hubble. And in blue, this is the actual model, which enough to convince you that we had detected water in there. But you see CO2 in there, and the point in orange was from Spitzer. You cannot really be sure that you have detected CO2 in there. But now this was observed with NIRISS very recently. And you can see just by eye, looking at how the transit depth varies with various colors. You can see the red points here, which are at 4.7 microns. They're less deeper than those at 3. And you can measure that very accurately. And when you translate that into a real transit spectrum, well, there you go. This is the CO2 feature. There's no ambiguity. This thing is real. And in fact, this little slope here, may not tell you very much, but a keen eye will tell you, oh, that looks very much like the signature of water. And in fact, there's another observation that is coming in very soon. This is from NIRISS, and it will be published very soon. It looks very much like this. So the water feature of this planet is very clear. Okay, so those are what I would say easy targets in terms of transit spectroscopy. What we're interested in is to look at a lot more than that. But before I mention this, let's mention that Canada has 5% of observing time with Webb, and we have 450 hours of guaranteed times, and we're involved in the early release science programs, and there's been about something like 300 proposals that have been accepted in the first year by Canadians. So I just want now to just finish my talk here very briefly about the TRAPPIST-1 system. This is the rock star of all exoplanet systems. TRAPPIST-1 is a very small star, not much bigger than Jupiter, that have 7 transiting exoplanets. And they all have the same size and mass as the Earth, roughly, and 3 of them are right in the habitable zone. So this region around the star where it's not too cold, not too warm, to have potentially water at the surface of this planet. So the big question, all these planets, do they have an atmosphere? And we don't know that. And that's one of the big missions of JWST in the early days to actually do this. So we have a program, both guaranteed time observations. This young lady here, Olivia Lim, was allocated the largest Canadian program in cycle 1, 53 hours to look at these planets. So in green, this is the data that we already have on these planets. H is to come. So F was actually upturned last Friday. So to me, it's a very historical moment because this is the first time Webb take data, transit spectroscopy data of a potentially habitable world. And those data was acquired by the Canadian-built instrument. So I'm really excited. I just got a spectrum like yesterday. So is there a problem with my microphone? Seriously, I cannot talk about it yet, but it's going to take maybe a few months because it takes quite a while to analyze this data, and we've been working on this quite hard since July. But just to give you an idea that this is real, we're getting real data on the system, and Canadians are really forefront to do this amazing science. Okay, so I just want to finish by showing a latest picture that came actually on Halloween Day. This is the famous pillar of creations. So you can see it looks very We like a beautiful image. But I mean, when you see this thing, I mean, you see a beautiful image, right? But for me, when I see all these beautiful images in spectra from Webb, I see human faces, especially those two. So Julia Zhu was the software engineer at Honeywell who wrote every single line of code of the GS flight software. And of course, this guy, Neil Rowlands, who's been the technical pillar of this project for all these decades. So these guys are just amazing. If we can do science now in Canada and abroad, this is thanks to these guys at Honeywell. So on this, I'll stop here. Thank you.
I think I'll bring up the lights and let the questions ready for the mic.
Sorry.
We'll break the ice. Is it open? Yes. Thanks a lot, René, for this very exciting talk. I wish I was there analyzing the spectrum with you and the jaw dropped at the result. And thanks to CSA to have funded such a participation in international project of this scale. I mean, if it wasn't from CSA's, momentum and saying, yes, we will be part of this and accepting the claim from the astronomers that we can't, be left out of the James Webb project, I think it would have been a big mistake, and I'm very proud to see that it's delivering results. It's an astronomy questions, but with all these large-scale gravitational lensing, are we starting to be able to create maps of dark matter and then compare that to the maps of the visible matter and see differences and things like that? Is this a new field that is benefiting a lot from the James Webb measurements?
Yeah, so we can, because we have so many details with James Webb, we can indeed make very detailed maps. You can, using these arcs, make a much more detailed map of the dark matter in there. And yeah, and that's these projects are actually in parallel, and you can use that to predict where you expect to have strong magnification and where you should see objects. Yeah, Webb will definitely help us to do much better modeling of these lensing. And you're right. I mean, CSA, of course, was a major partner there. I hope that it's going to be kind of in the given for everybody in Canada that this thing is not just NASA, and this is us, the CSA, and the whole Canadian astronomical community and industry together to do this incredible mission.
Well, I got a question.
Sure.
A naive question.
It could be for Neil too, as well.
Neil,
Yeah, you can join in.
Go ahead. The
question is, so one of your first images was sort of the time-related one, and how James Webb will enable us to look back in time. So what interested me was it seemed like that was in a particular direction. It wasn't sort of in any direction. It was in a certain direction, and it's going to, the beginning, to the Big Bang. So that assumes that the direction in which we're looking is the furthest away we can look.
Yeah.
I guess, but I don't understand this.
Well, first of all, the diagram that Neil showed is a way to illustrate the thing, but the early universe is not in a specific direction, it's actually everywhere. But we're not going to look everywhere. We're looking in some specific region of the sky that has been well studied in the past. The Hubble Deep Field was chosen because it was observable most of the time by Hubble, but also because it was away from stars. I mean, I love stars, But for the early universe, you want to have regions of the sky where you don't have any stars that really blinds you. And so there are some special fields that we call deep fields. There's in the northern hemisphere, southern hemispheres, and new deep fields that now have been created specifically for James Webb. And we're going to be looking at those specific regions. But essentially, wherever you look, and we saw that during commissioning, we see galaxies. They're everywhere. And all these blips of background objects are galaxies, every single one of them.
So the relative age is determined by the spectrum?
Yeah, so by the redshift, so how far the galaxies are. And right now, we're already going something like 500 million years after the Big Bang. So that's the main missions of Webb, to find out how these galaxies got to form. So one thing to mention is that after the Big Bang, there's this period of about a few hundred million years where there's nothing in the universe. All there is gas, hydrogen, and helium, and then but there's the density varies, and because of gravity, these things just compress. At some point, flip, you have the first stars lights up, the first galaxies, and we think these things occur a few hundred million years after the Big Bang. So we're already seeing stellar systems are fairly well formed and evolved 500 million years after. So this is what Webb is going to be pushed, to see these very first galaxies, and we're not very far from that. Yeah. Yes?
What is the hope for the furthest back that will be things?
Well, again, it's probably about a few hundred million years. After that, I mean, we know that the universe, there were not any stars. So I guess how we're going to see this is you're going to see, even though we see lots of galaxies, as you go back in time, you're going to see a drop in galaxies. This is when, okay, it looks like we found the very first galaxies that started to form at that time. And there's all kinds of open questions. You know, the black holes, they seem to be forming fairly fast, and we don't know why, how, and Webb will inform us on this.
So there are multiple theories as to when that date will be, and people are like waiting to see, right, or whatnot? Or?
Well, I mean, we need to acquire data, and this is what Webb is going to do to answer these questions.
It's a question for both you and Neil, and well, for having Webb functional guy, if you had to make lessons learned symposium about this whole adventure, what would it contain? The first topics of.
Well, get involved early. And we did it for Webb, and so I mean, we're already planning other big missions, and right now it's Canada is there, but not completely. It's because CSA early on really expressed their interest to be part of this, and this is how we got in there. But that's my main lessons learned. Start early as possible. It takes basically 20 years. By the time you have an idea of a new space missions, before you get the sky, it's 20 years. Yeah. Yeah.
So, anytime I've read an article about James Webb, and even your presentations today, you'd show a great, beautiful picture of James Webb, and then a not so beautiful picture from Hubble, which is also still kind of beautiful. So I guess my question is, does anybody else feel bad for the Hubble engineers? Because I kind of do. Because they're always being compared to. And I guess my second question then is, how are you planning to use Hubble in concert with James Webb? Because they're both going to be existing observatories for the next foreseeable future, especially if they service Hubble.
Okay, well, first of all, we're not trying to say Hubble is bad. No, we're just saying that Webb is way much more powerful than Hubble, which is already very powerful, Hubble in itself. So that's the main point. Now, well, Hubble remains mostly an optical telescope, right? And in particular with the UV capability, and we don't have that on Webb. So it's very complementary, and in fact, because of that. Our main priority in Canada in space mission is called Castor. This is basically a Canadian-led space telescope that would do UV astronomy, the same size as Hubble, but wide field to have complementary science to James Webb. I love infrared, But in reality, we need all wavelengths from X-ray, gamma, radio, and so Hubble is optical and a little bit of infrared, not as optimized as Webb, of course. So it remains extremely useful, but until it fails. When it fails, I don't think NASA will have another servicing mission for it.
Yeah, makes sense. Thanks.
Yes. Well, that's a big question. So, will Webb find evidence of life? It's a big open question. Personally, I think it's a long shot. I think Webb will be able to detect atmospheres of these planets, probably detect water in them, but whether it detects a biosignature is very speculative. But we can calculate how long it would take, and this is extremely good fractions of Webb time. But it's these kind of questions. I have to go back in time to look at to ask the same question for other observatories. Whenever a new observatory is put together, and you ask the question 5 years, 10 years after, what was the biggest discovery of this observatory? Well, you know what? Nobody anticipated. So I presented to you incredible signs that we're already planning to do with James Webb. But the big discovery, I don't know. It's something that will surprise us all. So for life, well, I don't know. We may require another instrument on the ground, the giant telescope to do this. But Webb will definitely pave the way. This is the first time we're going to probe the atmosphere of the TRAPPIST-1 system. Maybe there's no atmospheres around these planets. These little stars, even though they're small, they're very active X-rays emissions that may erode the atmosphere. So, and over the billion of years, maybe whatever atmosphere they have in there is completely gone. But even adding the answer to this will be a big, big deal. And the good news, we'll have the answer probably in a couple of years.
Yeah, I was wondering more on the image processing side. So when you take an image of a deep field of galaxies, you see hundreds or thousands in the frame. How do you make sure that you analyze all of them and determine if one of them is the oldest one that you've ever seen? Is it something that people go over manually, or do you have automated ways of determining that?
It's a good question. It's a very complex process, the image processing, because these images look very beautiful, but the raw image are not so good. There's lots of artifacts. Neil showed the moving target thing. There was these hot pixels, so and we know where they are. And so the way to correct for those is what is called dithering. So when you observe, you basically move things around, and so any instrumental artifacts in the detector can actually move, and you can correct them. So it's a very complex process, but we have decades of experience with Hubble and also on the ground to do this. I would say it's relatively easy imaging, but the spectroscopic data, the one we got, for example, this is completely new. We've never had this kind of data before, and so we're really on a steep learning curve right now to learn how to use this data, and this learning process will last several years. Yes.
What's next after this? Are people planning the next mega space telescope?
Well, yeah, I mentioned, here in Canada, CASTAR, this is our highest priority. This would be Canadian-led with international partners. But on the NASA side, there's a project called LUVOIR or ABEX. LUVOIR is a very ambitious project, which would be basically a James Webb-like telescope, not 6.5 meters, but 8, even 12 meters, operating mostly at optical wavelength, and designed to actually not only to take pictures of exoplanets and take their spectra. It's basically a mission to detect biosignature. So it's already in discussions, and this is why we need to get involved right now, because there's a lot of expertise here in Canada on this field, and we can be there in 20 years if that mission is actually chosen. Well, you don't see it. So we know, I mean, of course we observe stars that we know transits. So if the orientation is such that it doesn't transit, we cannot see it. Well, you don't see a transit, and so you don't observe them. And so there's a lot of exoplanet systems we know are not transiting. In fact, if you take a volume of stars, there's only 1% of chance that it will transit. And so, of course, we only observe those that transit. But there's so many stars, so many exoplanets. So we have a long list of transiting systems. But the habitable one, not that so. It's about a handful of objects that we have to observe right now. There will be more discovered in the next few years. But right now, we have this short list of a handful of transiting planets that are known to be in the habitable zone.
How locked in is the next, 2-5 years of telescope time on campaigns? Like, is there flexibility to adapt to a new discovery and repurpose time?
Absolutely.
Like, in the next 5 years, plan to all these PIs and all these research projects doing this?
No, the observations are planned on a yearly basis. So we all apply every year. The next deadline will be January 27th. So we apply for time, and then the proposal accepted, and then Space Telescope Science Institute, they basically make a schedule. But if you have a great discovery, something you'd like to do, you can write what we call the director of the discussionary time. There's 10% of time allocated for this to actually execute a program right now. And so there's other flexibilities, and of course you need a flexible observer because these transiting exoplanets, you need to stop everything when they occur. We know when the transit occurs, so we need to stop everything and tell the telescope, go there and start observing. So typically we spend as much time in transit and out of transit to have a baseline. So of course the observatory has been designed to accommodate these kinds of critical events like this. There may be a supernova exploding somewhere in a galaxy, and you won't observe it. So the telescope can actually move relatively quickly. Yes?
Do you expect James Webb to find older bodies than the quasars and black information that you showed today? Or are we sufficiently far back in the history of the universe where you are not expecting to see completely black information to go further back?
I'm not sure I understand. So you're asking if I...
If you're expecting to find older galaxies in the James Webb telescope than the ones that you showed already.
Well, all galaxies are, on average, relatively nearby, so we can observe them easily, of course, and with lots of details. And so those we can observe easily, yes. In much more detail, in fact, than early galaxies, because they're far away and, we lack details in them.
Sorry, my question was, are you expecting to find older galaxies in the James Webb telescope, even older ones, now that you have the resolution power, or the ones that we see?
I guess you mean earlier. Well, right now the record is something like 400 million after the Big Bang. So yeah, we have the capability to go further back, actually. Yeah. It depends on the mass of the galaxy, many things, but already a few months after, we already have, from existing data, already objects that looks to be very far. It needs to be confirmed with spectroscopic observation, but it looks good. Yeah, sure. Yeah, you have other sessions, I think.